dimensions by adding both space and time, and we see waves. So this will be sections 16.9 and 16.11 from your text. We will be talking about mechanical waves in general this time. Then we will have sound waves in particular for another class. I would say next time, but that's not actually true because, as you know, next time I won't be here. So we have the guest lecture on Friday to talk about thermodynamics, and then Monday's a holiday, and so it will probably be Wednesday when we come back for sound waves. So types of waves, or some examples listed in the PowerPoint for you. I brought actually a slinky with me, which I can use in a minute to demonstrate some different types of waves, a different way of classifying them. One way you can classify them is you have mechanical waves, you have electromagnetic waves, which is radiation, which we'll see towards the end of the semester. There's also plasma waves, which are often a mix of the two. And the other way to look at them is basically how is the motion of whatever thing is moving to create the wave related to the wave's propagation direction. So there's two types of motion. You can have motion which is perpendicular to the propagation direction. You can have motion which is parallel to the propagation direction. And that's why I brought the slinky. I'll hold it more vertically. So right now there's actually basically one type of wave in the slinky. And you can basically see it moving through the slinky. This is a longitudinal wave. Basically the coils of the slinky are moving in a direction that's parallel and anti-parallel to the direction in which the wave is propagating. Okay. The other type of wave is what's called transverse, which is where we move the links in the slinky in a direction which is perpendicular to the direction of the wave's propagation. So the wave is still propagating up and down the slinky, but the links are moving left and right. Okay, so that is two types of wave propagation. So I'll write the words down again for you. So longitudinal, this is medium, we could say. That's medium moves parallel or anti-parallel. And maybe I should say and anti-parallel because really the links in this slinky are just moving up and down. So this is parallel or anti-parallel to wave propagation. And the other is transverse. This one you have a perpendicular motion. So the medium moves perpendicular to wave propagation. So some examples of each type of wave. quick example. This is sound waves. This is light waves or electromagnetic radiation. Okay. If you have a string, like on a guitar, and you pluck the string, that one is a transverse wave. So a wave on a string. There's also some that are a mix. So the picture that is showing here, the ocean wave, is actually a mix between these two. So in the case of your longitudinal wave, what you have is some media that is typically more dense and less dense, or higher pressure and lower pressure. So very often you have like a sound wave that's moving through the air. What ends up happening is you have your source, and the wave moves in such a way that you have very high density and then sort of lower density. Then the density increases some more, and then you have some higher density, lower density, and so on. Okay, so you have something like this. The wave is propagating in this direction. All right, this is a snapshot in time. If you took a snapshot 1 moment later, might have like this. Etc. Haven't drawn these two to scale because the distance between these and between later should remain constant. So I've drawn this one a little bit bigger. But this distance between amplitudes of the wave, and this is in a sense an amplitude. This is maximum density, maximum pressure. This distance between consecutive amplitudes is what's called the wavelength, lambda. All right. For the transverse waves, your motion, maybe it's a wave on a string. Your motion might look like this. You have your taut string. When you plucked it and let the waves run, or if you grab the end of it and pull up and down, let them propagate, what you end up having is that the string takes on some sort of a shape like this, where your equilibrium unplugged string might be like this. All right? So this is your transverse wave. Now, there is also a wavelength for the transverse wave. It's the distance between consecutive peaks. Okay. So that's a new term for waves. That's different from what we had with oscillators. In addition to having wavelengths, we retained many of the old parameters for an oscillator. So there's still such a thing as period. There's frequencies. amplitude. That one's easiest to draw on a transverse wave. This right here would be the amplitude of the transverse wave. This maximum displacement. For a longitudinal wave, there's also an amplitude. I can't as easily draw it, but I will describe it for you. It is basically the maximum amount of pressure difference from the equilibrium pressure. Or if you'd rather, it's the maximum amount of particle density difference from the equilibrium density. The two obviously are related by the ideal gas law. All right. For what it's worth, both types of waves can be described as a sine wave of sorts. All right, so both types of wave we can describe using our wave parameter, and it's equal to some amplitude times sine or cosine. And usually we use cosine kx minus or plus omega t plus some phase. All right. That plus some phase means that we could also describe this as a times sine of kx plus or minus omega t plus a different phase. So which of the two you choose to use doesn't especially matter. What you typically find out is that there's actually 4 ways of describing a typical wave like this. One uses the form that I put there, cosine and a phase. One of them uses exponentials, which we won't worry about. One of them uses sines and cosines, but no phase. And one of them uses what's called a complex amplitude, which we really won't worry about. All right, so our standard form in here will be this form, because at a glance, the parameters that are present are easiest to describe. Here's what the parameters are. Well, A I've already defined here as amplitude. X is basically your position along the wave. All right, so you can think of this as maybe being a graph. Here's X. Here is your wave parameter. For a string, you might use a Y, for example, to represent how far has it deflected from equilibrium. For a sound wave, a longitudinal wave, you might use a pressure or a density here. For an electromagnetic wave, you might use the electric field and magnetic field strength. So this term right here, I'm using as an arbitrary term to represent whatever type of wave we have, a generic wave. All right, so define these two terms. We define this one as a position. T is a time, so this is position, time. You can think of those as your 2 other variables, your 2 independent variables, in fact. So your wave has not 1 but 2 independent variables. So this becomes a snapshot, in other words, of the wave. This is like if you took the guitar string, had a very high-speed camera, took a picture at a moment in time, the string might look like this, for example. A moment later, it will have a different phase. Shape will stay the same, but the phase will shift. So a moment later, you might have something like this. So the wave has moved from here to here at 2 steps in time. This right here is your phase. We already discussed that last time. Why is there phase? For a wave, why is there phase? You may have plucked it, not when you started your timer. you may have plucked it not at the position x equals 0. So you may need some phase for that. Omega, we already have. Omega is 2 pi over t. It's called the angular frequency. It's also equal to 2 pi times variously either f or mu, depending on whether we're doing a mechanical wave. Usually we use an f, or light, in which case we usually use mu. But it means the same thing. It's just how many oscillations or cycles per second. K is another new parameter. Right? So we've actually introduced two new parameters here. One is lambda, the other is K. K has the value that is analogous to this angular frequency, but for space. So this one is 2 pi divided by lambda, 2 pi divided by the wavelength. The job of omega and of K is to make sure that if you either go forward by one period in time, or at the same time move physically by one wavelength, that you will have gone through exactly one cycle of the wave. In space, you scan along like this, you go through one cycle, means you've gone through one wavelength. In time, you could think of any given point on the string as if it were a simple harmonic oscillator that's moving up and down like this. Right, so in time, one period means one oscillation of that point. And in fact, one model for these mechanical waves is to treat them as a series of coupled harmonic oscillators. So you could, if you so desired, imagine there being little springs at each point. That are attached somehow to the string. And I should add, the springs have equilibrium length when the string is in equilibrium. So we've now introduced some new parameters. There's a few more that we're going to look at. And specifically, we're going to focus now mostly on wave on a string. Before we do, there's a couple additional notes to be said about waves here. The first is they don't generally actually transport matter or media. So even though you see an ocean wave with all this water moving, the water itself, most of it, is just making some motion like this. It's actually kind of loop-shaped. There's a longitudinal motion, because the waves are going this way. There's a transverse motion like this. The upshot is that what you see looks like waves propagating this way. But for the most part, the waves do not actually propagate this way. The water, for the most part, is staying in the same spot. How do we know this? Well, because if you go to the ocean, and if the water was all actually moving this way continually, the ocean would move. You get a little bit of motion because of the tides. That's from shifts of position of the moon. That's from tidal forces. But for the most part, the ocean stays put. For the most part. Okay, there are some exceptions here. There's the big exception of what happens when there's a tsunami. Then a big part of the ocean does not stay put. Although eventually maybe it drains back to the ocean. But there's a smaller example which is actually shown in this picture. This is one of the reasons why I like this picture for this. Which is that the wave can move some matter. In fact, there are two things being moved by this wave. One is the surfer himself. The other is that this foam, the foam spray, is actually being moved. This motion of the foam spray is what's called wave breaking. Okay. So you can get a wave to sort of do work on something, and therefore accelerate it, move it, etc. Implication, waves do carry some information. Specifically, they carry momentum, and they carry energy, and they can therefore transfer momentum and energy. Okay. So the medium itself isn't moving, but it may transmit some energy to something else and therefore move that something else. Another thing about mechanical waves specifically is that in order to have a mechanical wave, you need to have a medium to actually carry a mechanical wave, and then you need some source of disturbance that produces the wave. So for your water, right here, your source, this doesn't show up so well on the projector, but basically somebody has thrown a rock here, so there's a splash. That was your source of the disturbance. Your medium is the water. You get these little ripples outward from that point. For what it's worth, if you want to do a test as to whether or not you're actually getting matter moved by these waves, you could throw something like a rock and then have a cork somewhere out here. And what you'll see the cork do is basically bob up and down. And it may wiggle a little bit this way, but as long as you don't have an actual current in the lake or wind or anything like that, the cork will more or less just stay right here as it bobs up and down. All right, so we've covered enough. There's some pictures in the slides. You have access to all these, but it's basically similar to what I've drawn up there on the board and discussed already. We have enough information, or maybe, to try and take one quiz. It's in short answer mode because this quiz has A through F, and your remote only has A through E. All right. So here's the answers you all come up with. It looks overwhelmingly like people have either picked that it will be shifted to the right. This knot will somehow be over here. Or it's in the same location, means the knot will appear right here 1 second later. How did you all arrive at those answers?
Well, the knot's not, it isn't traveling along the string, so it's in a fixed position, so it would be essentially the same position.
Okay, so because it doesn't travel along the string, it can't be over here. What does the string do? Yes?
I put it lower because, I mean, basically the difference is it would switch positions and it would kind of just go lower. It would be like in the same general area, but it would be lower.
Okay, so maybe you looked at this kind of cluttered diagram, pictured it here or whatever, and then a moment later pictured it here. Something like that.
Or just like kind of like look around, but like kind of just going like that.
Okay. So you said, all right, a second later, everything here should shift as far as the wave is concerned, but the string itself doesn't, and therefore, if this point shifts to here, then this has to drop, something like that. All right. Yes?
Even if the, like, if it changes, it's 1 second later, so maybe it has come back to the first position. So would that be something?
Maybe it has. Will it have actually come back to the same position in 1 second? You're right, it could, in that time, have done this sort of thing. It could also have done this sort of thing. It could also have just made it to here. Stretching. All right. Anybody else? Oh, you do have something. Okay.
I don't, it could also be F maybe because we don't know what the period of the wave is, so we don't know how long it would take to get to the middle point or the bottom.
Ah. Yeah, we don't know, as I just demonstrated, we don't know how much of this motion is going through. And you're right. The piece of information we need is the period. Or we could use the wave speed and wavelength, but that's less efficient. So lacking knowledge of the period, we have no idea where it will be. It might be the same place, it may be a different place. Depends on how much oscillation is happening in 1 second. All right, so let's scroll down and, oh wait, there's no scrolling down. Nobody picked that. Uh-oh. All right. For what it's worth, I mentioned to you that you could have the period or the wave speed and wavelength. The reason for this is that you can calculate the speed at which the wave travels, and the simple calculation is that it is the wavelength divided by the period, or it is the wavelength times the frequency. So V is lambda over T, or lambda times F is speed at which the wave travels. You'll use that this week in the lab, actually, because today, tomorrow, or yesterday, depending on when you have the lab, you're supposed to measure the speed of sound in a tube. And to do that, you'll be measuring, as it turns out, lambda, the wavelength, and F, the frequency, is actually given to you, but in a sense you're measuring. Okay. You can also, for what it's worth, rearrange K and omega, and from those you can obtain the speed. I'll leave that as an exercise to you all. All right. Something to be said about this speed. There's a few footnotes of sort. One is that there's actually kind of two speeds that you may say a wave has. There's what's called a group speed or group velocity, and then there's what's called a phase speed or phase velocity. We're not terribly concerned with the difference in this class. We're treating every wave as if it has only one frequency, one wavelength, and therefore the phase velocity and group velocity are the same. In more advanced classes, you see it maybe briefly in my waves and optics class, there can be a difference between group velocity and phase velocity. This is basically what happens if, instead of having a single wave like this, what if you have many waves together trying to travel down the same medium, and each one has a different wavelength? Well, then you have a sort of phase velocity for your carrier, but you also have a group velocity, which is the one that actually has the information of momentum, absolute displacement, etc. All right? So for our purposes, we just use lambda over t, or lambda times f. Second thing to note is that we now have two different things which mean speed. On the one hand, you have wave speed, the speed at which the wave itself propagates. On the other hand, you have the speed that we obtained from last time. What happens when you have an oscillation? You have something that's moving up and down like this, for example. Maybe your string, segment on the string. Maybe the knot, which is the back of page. Hello? Maybe the knot is moving up and down. Maybe the knot is moving left and right. You could put like a bead in a longitudinal wave, for example, very light bead. So you have some speed v at which that is occurring as well. That will not be the same speed that we have here. So very often wave speeds like this, instead of using a v, we'll use a c. Okay. Now c, usually we use in this context when we're talking about light, but it works as an adequate placeholder for other waves to distinguish between change in the wave's position per unit time as opposed to the change in a given point inside the wave per unit time, an oscillator. How do you determine each? Well, C is this. To get the other one, the speed at which that little point is moving up and down, basically you do similar to an oscillator with your wave. So if this right here is your wave, then the speed of each thing within the wave would look like V is negative A times omega times sine kx plus minus omega t, etc. So that's the speed at which you're not moving up, down, left, right, whatever you have. This is the speed at which the wave itself propagates. Your book, for what it's worth, just says V in both cases. So if you want to follow what your book says, you write a V in both cases and keep track of which V means which thing. If you want a notation that lets you distinguish, then maybe use a C here and a V here. Likewise, by the way, you can figure out what the acceleration of that knot is by going one more down, and you have minus or plus a omega squared, cosine, etc. Now, some of you may have noticed that I've written plus, minus, minus, plus here, all that. That is because the sign that's in this guy right here, the plus or the minus, determines which direction the wave propagates in. If you have a minus here, it propagates to the right. If you have a plus, it propagates to the left. All right? And then the sign gets flipped over here. So if it's plus omega t, it'll be minus omega t here. If it's minus omega t here, it'll be plus here. This sign and this sign will remain, however. My clicker is not scrolling correctly. All right. So let's have a rematch of this question. This time, you're given a period. Now note, I've changed the amount of time between snap. All right, let's go ahead and close it. See what you put. Ooh, reversal of our answers from the last time. Suddenly everybody is picking C and D. So that is higher or lower. Some people have said same. Some people have said to the right. All right. Just been kind of steadily moving over this way, so I guess this would be Bethany.
I'll put it lower, but I was thinking this, so.
Only a guess?
Yeah.
Okay. Man, your row is offset from the other two. It's like a shift of the desks all of a sudden. All right. Well, let's go one more over then.
I said higher, but I don't know what I see.
So we have one guess for higher and one guess for lower. One more over.
I said lower because if the period is 2 seconds, 1 second later, then it would have gone to half of the sine wave.
Tried to draw everybody's attention to that too at the start. Maybe you didn't hear me. Okay, so I guess you get a bye. Yeah. Okay. I mean, you had an explanation, just for the wrong time. Okay. So what? We jump back over here. Might as well finish the row. Yeah.
Yeah, I think yeah. I said to the right just because whenever you drew that earlier, you were like, it's to the right, but yeah, really.
Okay. All right. Next row. Yeah.
I just put higher because I was guessing.
Yes. All right.
Can it be lower because it can be right or left, but if you check like after 2 seconds it will be in the same position, but either way if you take the half time it's going to be lower than where it is.
All right. Is it a confident lower or a not confident lower?
Kind of.
Kind of confident lower. All right. Oh, Sydney?
I said lower because I assumed that if that would be half, that would be half of the period. So we going downwards.
So the same thing that she said,
Yeah.
but it's not a half a period. It's 0.1 second. The period
I'm
is 2
saying the
seconds.
position it's in is half of a period, it does not include. So 0.1 second after that would be lower.
Okay. Yeah.
I put higher because it's 0.1 second. So I just figured it's sparking up just a little bit more.
All right. Anyone else? In the back?
Yeah, Brian, I was gonna say that there still may not be enough information because you don't know. Like she was saying, like you don't know where the knot, like what time the knot was in the period.
Okay. You've overreached this time, though. There is enough information this time to do it. It trips it. But you're right last time. So you're still batting 500, which is better than most people have done over the course of the day, as you guys will figure out if you haven't already. All right. Nobody else? It's not your turn yet. Go out. All right. So here's a quick little drawing of it. Now notice where the hand is. The hand is the source of disturbance, so the wave has to move away from the hand. That tells us that the wave is moving in this direction. So at this particular snapshot in time, the knot, it's not a very good drawing, but the knot is like right here. The wave has to move this way. Okay? So that means that in a moment the hand has to be here. Now this is not necessarily to scale with our 0.1 second, but we do know that it is less than a half period. In a half period, this point will be down here. Right? Even if we draw one that's really close, like this, as our half second, or as our 0.1 second later, track it along what this thing's actually doing. Etc. Now the string itself, each point on the string is a transverse wave. The string is just going up and down. Implication, the knot is just going up and down. So we need to draw a vertical line through the knot. And where that line intersects the green line, that's where we expect the knot to be. So this vertical line seems to intersect the green line somewhere in here, which makes it lower. So the answer is D. There's some other wave parameters that are in here. You may use them a bit in your homework. For example, you can figure out how much energy is being carried per wavelength for a wave. It's usually given by 1/2 of the amplitude squared times some parameter. Same form, by the way, as with a simple harmonic oscillator, where it's 1/2 times the spring constant times the amplitude squared. The difference is that this epsilon term maybe has, it has the same dimension in some sense for the same reason as the spring constant, but it's a wave, so we don't actually necessarily have a spring involved. There may or may not be a definable spring constant. There is, however, a definable amount of mass in one wavelength, and there is a definable frequency. Okay. The one other thing that you needed to get out of today is wave on a string, the parameter for determining the propagation speed. We'll encounter this again in the lab actually next week when we do waves on a string. Okay? We can say that the speed at which it propagates is the square root of the force of tension divided by the mass per unit length. Right? So that first equation is the tension in your string. Implication, maybe you have a string that's attached to like an agitating bar or something, like what you'll have next week in fact. Now you have your string, you run it over a pulley, and you have some mass attached. How much tension will be in the string? Well, you have a mass here. The mass has force of tension up. It has m times g down. It's at equilibrium. Implication is that the force of tension is how much mass is attached to the end of this weight. We have to make a distinction here, though, because there's also a mass term that shows up in here. So this is like your hanging mass. Mu is what's called the mass density of the string. That would be the mass of the string divided by the length of the string. It's the mass per unit length. Okay, so you need to measure how long is the string. You have to measure how much mass does it have and divide the two. That gets you your value for mu. When you put the two things together and take a square root, you get the speed at which the string propagates. So I'm sensing that I'm out of time for today. So I guess we will stop there. And if you are in my lab,